Hello.
Hey, Miss Jocelyn, how are you?
I'm good. I made
Good.
pancakes this morning.
You did what this morning?
I made pancakes.
That sounds delicious. I like pancakes.
I stuffed myself to the brim with pancakes. Because while I was making them, I was eating them.
That sounds awesome. Hey, gang, come on. They're coming. They're just slow today. Everybody's chit-chatting. Here they come. Hello. Ozzy,
Our
look
girls
at
across the
here.
street this morning.
Come on, Ozzy. Ozzy.
Miss Annie.
I think they're.
It was so cold this morning that the ground looked frosted over. Like you could see like a thin
Is
white
it really?
layer over the grass.
It's not as cold here as I expected it to be, but it's cool and wet, which is not awesome, but
It's sunny.
you got the sun, huh? We don't have the sun. Maybe walk around, Eleanor. I think Alec didn't realize you were going beside him.
I tried that way first.
Hang on, Drew. Let Eleanor through before you get situated. She's trying to get back there. There we go. Miss Lowe.
It probably didn't work because I was running my backpack with it.
Yeah. So I think the D'Antoni girls are going to be out for one more week, unless they come today. Are they coming? Okay, cool. I wasn't sure.
Who?
Ella and Jules.
Yeah.
Wasn't sure if they were going to make it today or not. Glad that they'll be here then. And then Traveler will not be joining us. No, we waited for him, but he will not be joining us. So they're done for good. They decided they're not coming back this next semester. So
Who? I'm sorry.
any of the Levies. So Trav, Kai, and Ivy are gone.
Oh, no.
Yeah, I know. I was very sad, but just so y'all are. Oh, somebody bump it because now it's out of focus. Let me see if I can adjust that a little bit. Sorry, I'm real big right in your face there, Justin. All right, there we go. Okie doke. Well, while we're waiting on them, did I just lose my ice pack? You know me, I'm always got ice packs everywhere. Even though it's 40 degrees, I have to keep myself cooler. I get crazy. All right. So here we are. And you guys had another quick lesson, right? We're trying to get ourselves all caught up with the other class so that everything is in line. And we've kind of rearranged our seating here a little bit because there are now going to be fewer of us permanently. So due to that, we can compact a little, but I'm trying not to compact too much. Actually, if you want to scooch over, Eleanor, to space yourself, you can. Unless, okay.
I'm fine.
All right. Huh.
That's fine.
Oh, you're bad.
You can do it. No, it's fine.
And I'm hoping that Senya comes. Senya broke her foot.
Senya broke her foot?
Senya has a broken foot. So I hope she still joins us. I know. And it's really sad for her because she's a dancer and she broke it in class and now she can't dance for several weeks or days or whatever. So that's going to be a serious bummer for somebody who is as committed to dancing as she
When
is.
it grows back, will it be bulky or something?
Say what?
When it grows back, the bone grows like unnaturally.
Yeah.
It'll be a bit different dancing.
Sometimes, yeah. They actually call it they actually call it dancer's fracture. So it's not
used to breaking bones.
not
Sister did it, like,
surprising.
every
I know
6
your
months.
sister was constantly in crutches. So
They said
Hey, Miss
whenever
Sky.
she went to like the children's healthcare.
Sky's
Oh,
here.
sorry.
Actually, if you want to, you can sit on the end if you want, Sky, because I think they switched to part one. All right, awesome. How you doing? You good?
Oh, the children's healthcare Valena, they knew my sister by name. And they were like, you again.
I'm not
They
surprised.
almost named the X-ray machine after her.
I'm not surprised that they know Natalia by name because she was always there. All right, well, let's start with our lesson. It's not a very long lesson today because, like we were saying, you guys are just trying to kind of catch up with the others. Okay. So what we're doing today is we're doing a little more discussion about, how did I do that already? 19. So this is going to be enthalpy, intermolecular forces, and states of matter. So here's that word intermolecular again. And we talked inter and intra a little bit last week, right? Do you remember what inter versus intra meant? Who remembers? No? So inter goes in between things and intra goes inside something, right? think the example we used was an interstate, goes between the states, right? And then I think the intra example we found when I started Googling to see what autofilled was intracranial hypertension. Do you remember that? Which ended up being like high blood pressure inside your skull. So that's probably not something you want. So yeah, so intermolecular would then mean forces in between molecules. So it would be not the elements within a molecule, it would be the molecules within a substance. So what keeps all those molecules together, right? And then states of matter. So let me ask you this. How does it feel? How do you feel when you're excited about something? How does it feel to be excited?
I can't sleep.
You can't sleep, okay?
Like if I'm really excited for something, I will wake up either the same day or at like 12 o'clock at night, and my body will not let me fall back to sleep.
Wake up in the middle of the night, you'll do that too, and then you can't, yeah, exactly. So
I've once woken up at 10.
that's Rob. Drew, if he's excited, he goes to bed early because he thinks that he falls asleep and it makes the night go by faster than if he was awake waiting. So yeah, it's a good plan. I like it. It's a good plan. So yeah, so when we're talking about being excited, how does your energy level feel? Do you feel low energy and tired, or Jocelyn was just saying she can't sleep? What do you think?
I feel useful.
Very like energetic.
Energetic. Yeah, I think I would too if I was very excited.
It depends on what you're excited about.
True. So let's say you were so excited that you had so much energy that you were literally moving. You ever been that excited that you have so much energy? You're literally like, oh my goodness, something really exciting is coming. All right, so let's pretend we have a wall in this room and we're gonna shut ourselves into this room like a box, okay? And we're all very low energy. We're all very tired and we're all sleeping. If we had to try and make ourselves take up as little space as we could probably all compact ourselves over into one corner sleeping, right? We wouldn't take up a lot of space, would we?
Just sleep standing up.
Yeah, we could sleep standing up if you're really good at that. Mm-hmm. Right. And if we were a little excited and awake like we are right now and we're moving around, we need a little more space, right? But if we're super excited, we're going to need a lot more space, right? Imagine how much space you would need. They're here! Yay, Miss Jules! Oh, it's Jules. I'm so happy. Drew, can you scooch up or scooch out so Jules can get through, honey? There we go. And Ella. I'm so happy these girls are back. Jules, you are the survivor. You made it through. All right. You're going to have to share this experience with us.
Well, it's like a flu, but the thing is, the long-term effects are bad.
Yes. It depends on the person.
That's a good point.
Well, none of us have been there yet. So.
Oh my goodness, yes! She's much younger. Yeah, she's much younger.
She's fine.
I would have given you this, but
Any of us here except for getting the I got that. I got the long-term effects.
So tell us, Miss Jules, how was it? You're on the other side of COVID. How was it?
Not too bad. I had lots of headaches.
Mm-hmm.
I got very stuffy,
Mm-hmm.
but I got special treatment, so that was good.
Special treatment, and what was that like?
Plasma?
No, not plasma. Not that kind of treatment. Like, did you get to do special stuff in your room, or?
Well, first of all, I had to spend the whole day in my mom's room, wear a mask, run upstairs as fast as I could, and then just sleep in my own room, and then just go downstairs and just say good morning to everyone, and then just go to my mom's room.
Wow.
And that's how it went.
That's how it went, huh? How about you, Ella? Was it weird for you?
Apples and dulce de leche, which was amazing.
Ooh, apples and caramel stuff is good. Yep. So currently, I laughed at this, but I shouldn't. But I laughed at the response. So our priest, his wife has it right now, and he said Terry's in quarantine up in our room, and this is what made me giggle, behind the door of shame. He said, we're opening the door and shoving food at her like a prisoner. So, yeah, that's how it goes these days.
Just, here you go, piece of mango.
Yep. Well, I can't tell you how happy I am that you girls are back. I was worried about y'all. All right, so we were just talking about energy and how it feels when we have energy. And we were imagining that if this room was closed off like a box, right? And if we didn't have a lot of energy, we all just needed to lay down and sleep, we could spread out on the floor here. We wouldn't take up a lot of room. But Ozzy is changing my slides with his nose. Ozzy,
Oh,
goofy
Yeah,
dog.
that'll work a good
But if we were all laying, imagine us all laying out on the floor. We wouldn't take up a lot of space, right? And
I'd actually probably be very comfortable
yeah, she'd be comfortable. Jocelyn would be comfortable.
because I can fall asleep on the floor if I am tired enough or
yeah,
like
It
I don't know how, just the floor with a blanket on it. That is
Now,
that is
how do
comfortable.
we look as far as order goes? Do we look orderly or do we look
This is
disorderly? How would you imagine if we were all just laying on the floor still? Would that be orderly or disorderly? Kind of orderly. Now compare that to if we were all super excited, we all just had a gallon of ice cream and 5 pounds of candy and we're bouncing around this room like crazy. Is that going to be orderly or disorderly?
Disorderly.
Yeah, and are we going to take up more or less space being disorderly? Yeah,
We're
so
gonna be
that's where we need to think. All right, so when you're thinking about enthalpy and entropy, we're talking about order and energy, all right? So remember, enthalpy is about energy and entropy is about order. And if it helps you remember, there's an O in the word entropy, so that reminds you that that one's about order. So if we look here, and it says your enthalpy is your total energy. You girls good over there?
Yeah.
Your enthalpy is the total energy of the system. So if we were asleep on the floor, all of us in our little sleeping bags and nice, neat little lines, all orderly, would we have a lot of energy or little? We said a
little.
and simultaneously, would we have a lot of order? How would our order be? We'd be more organized. Okay, so when you think about entropy, it's really more about the disorder. So it's about the level of order, but it's about how disordered it is. So if you're all asleep in your sleeping bags and we're all packed nice and neat together, we've got low energy and high order, which means that our enthalpy is going to be low, right? And our disorder is going to be low because our order is high, right? Your order and your disorder are going to be opposite. So as you increase the energy, we're going to increase the disorder. So as your enthalpy increases, your entropy increases. So if you imagine us laying out on the floor, that's like a solid. If we're the molecules in a solid and we're laying in our sleeping bags in nice, neat little lines, and we have low order and we have low disorder, then we've got low enthalpy and low entropy, and it's like we're a solid. If we are like we are right now, we're just kind of moving around, right? We can move, but we're not crazy. That's kind of like a liquid, right? So our energy is higher and our enthalpy is higher then, and our entropy, which is our disorder, is a little higher. We're a little more disordered right now than we would be if we were nice, neat lines, right? And then imagine if we all had all the candy and the ice cream and we were pinging off the windows and dancing. Yeah. Well, we would have really high entropy because we'd have really high disorder, and we'd have really high enthalpy because we'd have a lot of order, a lot of energy. And then let me ask you this, what state of matter would that be? That would be gas. Good, Ella. And let me ask you one more thing. When you're sleeping versus when you're moving around a lot, how does your body temperature feel if you're laying all chill and relaxed versus running around? What's the difference in your body temperature, do you think?
I'd be much cooler.
Mhm.
You'd be much cooler because you're not moving around and creating
Right,
energy.
she said the same thing. You said the same thing. So if you're moving around a lot, you get hot, right? Right? Okay.
Right. Like when I dance, I get so hot I need to plop on the floor and literally just sit there for like 5 minutes so I can cool down.
Yeah, I agree. So she said, if I get really hot, I just need to plop on the floor so I can cool down. Totally. I'm sitting on an ice pack because I can't let myself get hot because my body goes, ugh. So, yeah. So why does your body temperature, do you suppose? Do you remember what temperature is? What was the definition of temperature? Do you remember what it means versus heat?
It's the amount of energy within a system.
What kind of
It's
energy
usually
specifically?
displayed in heat.
Kinetic, right? Kinetic. Okay. What kind of energy is kinetic and what does kinetic mean?
It's the energy associated with speed.
Not speed, but motion. Yeah, you guys are good. All right, so
So would
You're-
potential energy be sleeping?
no, if your if your temperature is high, you girls go over there. No, chit chatty. So if your energy is high, your temperature is high, and the reason your temperature is high because your motion has increased, right? And it comes down to stuff like friction, and I mean, think about that. If you put your actual the molecules within your body, when you start moving faster, you're moving faster as a product of them moving faster, the molecules within the cells in your body, and they're bumping into each other. It's really wild to think that it all comes down to motion of particles within you that you can't even see. Yes, Alec?
You slap a chicken enough, you can cook it.
If you slap a chicken enough, you can cook it? Of course, yes, of course, because it creates enough friction.
Sorry, piece, but it's someone did it and it got to 130 degrees.
Yeah, that'd be true. Yeah, anything that you create enough friction. Yeah, absolutely, create enough friction.
Slap a chicken all day, then you got dinner.
There you go. So here's something to think about when you're thinking about states of matter, okay, and heat. So as you increase the heat, you increase the energy or the enthalpy, and you increase the entropy or the disorder. They all move together. So your enthalpy has something to do with the energetic content of a system or a molecule, and your entropy has something to do with how that energy is stored. And usually it's not being stored very well if it's bouncing everywhere, right? You have lots of energy. So gas is like that. Remember, the particles in a gas are just pinging all off each other, right? So this last summer, I had a really weird experience with my van, and nobody has been able to solve the mystery. But here was the mystery. It had been sounding weird for a couple weeks, and I thought it was having transmission troubles. It was right about 100,000 miles, and I thought, oh, perfect, because that's when my warranty dies. This is when we're going to have trouble, right? So we went out to Lake Allatoona when his cousins were here. We rented a boat. We had a fabulous day. Then it rained. We came in on the boat. We were getting pelted with rain the whole time. It was hurting because it was stinging as we were running, right? I mean, it was rough, right?
I think it's like not to
Yeah, no, he did. So we finally get back to the van. We all get in the van. So it's me and Jason, both our boys, my niece, my nephew, my sister-in-law, and we're heading down the little hill to leave Lake Allatoona, and my van's making a strange noise, and then it goes, and then just stops working. And we coast to the bottom of the hill and pull into a little turn lane where we sat. So this man comes with a tow truck because it will do nothing. And he says, well,
I told you it was the oil. You didn't
well, he says, will you check the oil? Did you check the oil? And I'm like, not today. I mean, I had the oil changed when I should have had the oil changed. So he checks, there's zero oil. Okay, that doesn't usually happen. Usually it'll get low, or you'll get a light that says your oil is low. But why do you suppose there's oil in an engine? What's it for? What's the purpose
to
of
help
it?
it work.
Yeah, how
They're basically trying to
specifically?
feed it. It runs on.
It doesn't run on it. There are parts in the engine that move, and they move very fast. So what happens when you move something fast? If you do this with your hands, what's it feel like? It gets hotter, right? If you were to put like olive oil in there, would it get as hot as fast? Right. So reduces the friction. So the oil in an engine is supposed to reduce the friction. Well, somehow there was a leak in my system. We still don't know where, because there was no oil in the driveway, no oil in the parking lot, no oil anywhere, but somehow it just disappeared. I don't know. Nobody knows what happened to it, but it's gone. It apparated, as if that's, there's a scientific, apparated like in Harry Potter. There's a scientific answer, just nobody's been able to figure it out. So what do you suppose happens to an engine with very fast moving metal parts?
Boom. They melt together.
They melt together.
Eventually, boom.
Yeah, well, no, eventually is what you get.
Yeah.
So you have this engine that's moving really fast. All right, so you have a ton of enthalpy in your system, right? And as you're doing that, your entropy starts to increase. All those little molecules and all those particles within all the metal parts start to spread out. And they spread out, and the metal becomes more malleable. It becomes more bendable, like it would if you put it in a smelting iron. Like that's how they, you ever seen a blacksmith work? They put the metal inside a fire, it gets hot, and you can start to bend it. Well, that's what happens to all the parts of your engine if they get hot.
It gets hot.
Yeah, and it just went, and they call that freezing. Now think about it. Why would they call it freezing? We talked about states of matter. It stops, so that's one thing, like when you run, freeze, yep. But remember that literally freezing is, right, a liquid turning into a solid, and the engine parts don't go completely liquid, but they do start to get malleable, they do start to bend, and then it gets to the point where they lock up on each other because the shapes just don't work anymore. And at that point, your engine stops working and it instantly cools, and it is literally frozen, like the scientific definition of frozen. So I ended up having to get a new engine. End of the story. But when you think about how all those things go together,
Everything metal in here is frozen.
that's true. Everything metal in here is frozen. Everything solid in here is frozen. So think about this. So here's a graph for you, which y'all can see up there, I think. So here is our temperature versus our energy. And it's that little, remember the delta in front of energy? That's going to be your enthalpy, right? And then what are we, how are we measuring the energy? What unit are we using up there? What's it say? Can you see it from here? It says joules. Yay, like our joules. So remember, joules with an O, not joules without an O, but joules with an O is one way we can measure energy. So if you look there, it says right here, your change in enthalpy from, as you move up to a solid, it's you got an increase here, and it goes with your temperature too. Your temperature goes up, and then you have this point right here where nothing happens when it's changing from solid to liquid, and your energy is moving along, but your temperature isn't changing, okay? And then you have the same thing right here. What are these two flat lines, do you suppose? What do you think that would be? Right here, see if I can maybe, here we go. You see this right here? So what we have is we've got an increase in enthalpy or energy, same thing, right? And the temperature, see this temperature's over here, so that's increasing too. And then you have this kind of flat line where your energy is still moving along, but your temperature hasn't changed. And it says solid to liquid. What do you suppose you call this right here? What is it when a solid changes to a liquid?
That's where I'm melting.
No, solid to liquid is, oh yes, melting. Sorry, I thought, sorry. Yes, so this is your melting point right here. At your melting point, nothing, the temperature doesn't change. For a while, your energy is changing, but your temperature's not, you see? And then if you look right up here, what have you got? Same thing, but liquid to a gas. What do we call that? Well, what do you suppose you, yeah, it is evaporating. But what do you call this point right here? Do you remember? That's your boiling point. So if you put water in a pot and you boil it, how hot is it going to get? In Celsius. Make it easy. 100. Is it going to get hotter than 100? The vapor might. The vapor above it, so you shouldn't stick your face above it or your hand above it. Yeah, but I'm saying the vapor above it, that might get hotter than 100. But that water in that pot is 100 degrees, period. And it's going to stay 100 degrees. The water that you're boiling in the pot. If you're boiling water in a pot, it gets to 100 degrees. Whatever, yeah, whatever water is remaining is going to stay at 100. It's not going to get hotter than 100. As it turns to gas, it could be. Now I was about to get to boiling sugar. So I do a lot with sugar, right? For cakes and stuff. I did a cake this week. I'll have to show you. It's covered in sugar ice cubes because it looked like a bucket full of mini liquor bottles because this guy was turning 21. But anyway, sugar, when I cook sugar, I cook it to about 400 degrees, which is, it's not 400 Celsius, it's 400 Fahrenheit, but that's still considerably, almost twice. Yeah, and truthfully, sugar burns are the worst, and I'll tell you why. Because they hit you, they instantly stick. They stick and they start cooling and solidifying.
No.
And it will, oh yeah, oh yeah, it will. The only way to get them off is to try to keep your mind about you and not do this, because now you've got burns on your hand everywhere. You have to run to the water, and it's awful because your instant reaction is to knock it off, but then you burn everything else. So you have to run to the water and run water over it so you can get it solid and then flick it off. Meanwhile, it's like taking all your skin from it. I've got so many sugar burn scars on my hand. Yeah, I do have some, but I have very small hands and it makes it hard. So there's a bias in nature towards decreasing enthalpy in a system. Reaction can happen when enthalpy is transferred, and a reaction is favored if the enthalpy decreases. So we like to decrease enthalpy in nature. See where it says there's a bias? What's a bias? Do you know what that means?
It's when you're very specific and you're basically just kind of lean towards one specific thing.
No.
You
So a
like
bias is a
like something
tendency.
else.
Oh yeah. Okay. Yeah.
So-
You've heard it that way.
You
Mhm.
like something else, so you use it against that other person. Usually, if you have it.
So you probably heard it in this text of political bias.
Yeah, political bias. Political bias. You know, just know that, you know, a lot of political bias is happening. I'm gonna
Besides,
like,
it's one thing.
I'm gonna like start arguing about anything.
Right.
That's like the most common.
Yeah, you do hear political bias a lot. That's a word you hear. So a bias means your tendency to adhere to a certain.
Let's say you like one side. And
Yeah, it's your
It's hard to
tendency to
change.
believe something,
usually if you have
to
like
lean
one,
towards
it's hard
something.
to change.
So there's a bias in nature towards decreasing enthalpy in a system. So there's a bias in nature to cool stuff down. There's a bias in nature to slow down the motion. And why do you think that is? Think about all the energy we talked about for us in this room, right? If we were bouncing around the room, why would there be a natural tendency for everything to sort of settle down?
Gravity.
Mostly it just has to do with the fact that it's difficult to keep things in motion, right? I mean, there's that whole Newton's law with objects at rest stay at rest and objects in motion stay in motion. And then there's things to slow them down, friction and other forces that slow things down. That goes for particles too. It's hard to keep that motion going. It takes energy to keep the motion going. So there's a bias in nature to make everything slow down, right? And then there's also a bias in nature towards increasing the entropy in a system. So reactions can happen when the entropy increases. So a reaction is favored if the enthalpy decreases. Entropy, there's this whole kind of back and forth deal. And then, so here we go. If your enthalpy has to increase, then your entropy has to increase. So here's a little bear, and he says, I'm entropy. Nice name for a bear. And it says that's his minimum.
That's a bear.
Well, I think
It
it's a
looks
bear.
like Prince Flintstone and Harold.
No, baby, that's a bear. He's cute. So anyway, this little bear is.
That's like my.
Can you see him, Jules? Here, he's
What kind of
cute.
bear is that?
I don't know. He's a bear, but this bear.
It's like the jump scare game.
Oh.
He's so wise. He's like a
So his name is enthalpy, which is a rather. Come here, you. Which is a rather fancy little name, and he has to. It says it's just minimum enthalpy, and that's his maximum entropy. And so in order to get there, he has to go over this hill to get to the top of this mountain. So what this graphic is supposed to show you is that there's a natural tendency for a reaction to move to the side with the maximum entropy and the minimum enthalpy. So if one's increasing, the other's decreasing. So what you find when you have your maximum entropy, and because think about this, is it easier to keep your ring neat or is it easier to let it be messy? Right. What takes more energy? Keeping everything perfectly organized or just dropping stuff where it goes?
It's already perfectly organized.
Dropping stuff where it goes.
Oh, I think it takes more energy to make it super neat.
Yeah.
So
Well,
if you,
it's already super neat and takes more energy to make it messy.
so
Yeah, that's exactly why my room is a disaster area.
right. So if you live in a house with other people, and chances are all of you do, then what you experience is you have to do constant work to keep everything organized, to keep the clothes clean, to keep everything done, right? That takes energy and it takes effort from you. So there is a bias in nature to just let all that be as disorganized as you can let it be, but to also not have everybody going crazy. So this is kind of a weird process, but what you're looking for right here in the middle, is this tipping point, all right? And your tipping point is an equilibrium, which we'll talk a little more about right here. So when both your entropy and your enthalpy favor the reactants in a reaction, it doesn't occur. But when they favor the products, the reaction goes to completion. So when you're looking at an actual chemical reaction, it depends on whether or not you're going to have more disorganization and lower energy on the front or the back. So if you've got more disorganization on the front side of the reaction where the products are and low energy, that reaction isn't going to happen. But if doing the reaction is going to cause more disorganization, more organization and higher energy on the other side, then it will happen. So when they oppose one another, and it's perfect, nothing's going to happen, it's equal amounts on both sides, that's your equilibrium. And most things in nature as they exist, without having something done to them, are at their equilibrium. So all the gases that are floating around in the air, all the solids in this room, if it wasn't at equilibrium, it would be undergoing some kind of a process. And right now it's not. But if we cooled this room, super cooled this room, we would notice the gases starting to condense and, but the gases around us would start to condense and they'd start to become more solid. And so then you'd know that you're not at equilibrium anymore, right? So here's your little seesaws that show you. If your entropy goes up and your enthalpy goes down, your reaction is not going to move. But if you've got more entropy and less enthalpy, there you go, bing, bing. So you can kind of see it's sort of like a seesaw, and it gets complicated. It gets hard to envision. It gets hard to kind of process a picture in your head. But at your level, you don't need to know the intricacies of it. You need to know that it's a thing. And yes, it's a thing. And you're gonna, especially when you get to high school chemistry, which you all will have to do, you'll see a lot more of it there. And there'll be some wonderful equations that go along with it, with all these fun symbols. Everybody loves their Greek letters and weird symbols. So, huh? Do you? Well, there's a lot of those in science, right? Now, so part of your assignment was to watch this video, right? So we'll watch it again in case some of you watched it like a week ago or whatever, and it's been a bit. All right, so this was your homework, right?
There's a concept that's crucial in chemistry and physics. It helps explain why physical processes go one way and not the other. Why ice melts, why cream spreads in coffee, why air leaks out of a pressure fire. It's empty, and it's notoriously difficult to wrap our heads around. Entropy is often described as a measurement of disorder. That's a convenient image, but it's unfortunately misleading. For example, which is more disordered, a cup of crushed ice or a glass of room temperature water? Most people would say the ice, but that actually has lower entropy. So here's another way of thinking about it. Probability. This may be trickier to understand, but take the time to internalize it and you'll have a much better understanding of entropy. Consider two small solids, which are comprised of 6 atomic bonds each. In this model, the energy in each solid is stored in the bonds. Those can be thought of as simple containers, which can hold indivisible units of energy, known as quanta. The more energy a solid has, the hotter it is. It turns out that there are numerous ways that the energy can be distributed in the two solids and still have the same total energy in each. Each of these options is called a microstate. With 6 quanta of energy in solid A and 2 in solid B, there are 9,702 microstates. Of course, there are other ways our A quanta of energy could be arranged. For example, all of the energy could be in solid A and none in B, or half in A and half in B. If we assume that each microstate is equally likely, we can see that the energy configurations have a higher probability of occurring than others. That's due to their greater number of microstates. Entropy is a direct measure of each energy configuration's probability. What we see is that the energy configuration, which the energy is most spread out between the solids, has the highest entropy. So in a general sense, entropy can be thought of as a measurement of this energy spread. Low entropy means the energy is concentrated. High entropy means it's spread out. To see why entropy is useful for explaining spontaneous processes like hot objects cooling down, we need to look at a dynamic system where the energy moves. In reality, energy doesn't stay put. It continuously moves between bonds. As the energy moves, the energy configuration can change. Because of the distribution of microstates, there's a 21% chance that the system will later be in the configuration in which the energy is maximally spread out. There's a 13% chance that it'll return to its starting point, and a 2% chance that A will actually gain energy. Again, we see that because there are more ways to have dispersed energy and high entropy than concentrated energy, the energy tends to spread out. That's why if you put a hot object next to a cold one, the cold one will warm up and the hot one cool down. But even in that example, there is an 8% chance that the hot object would get hotter. Why doesn't this ever happen in real life? It's all about the size of the system. Our hypothetical solids only had 6 bonds each. Let's scale the solids up to 6,000 bonds and 8,000 units of energy. And again, start the system with 3/4 of the energy in A and 1/4 in B. Now we find that of A spontaneously acquiring more energy is this tiny number. Familiar everyday objects have many, many times more particles than this. The chance of a hot object in the real world getting hotter is so absurdly small, it just never happens. Ice melts, cream mixes in, and tires deflate because these states have more dispersed energy than the originals. There's no mysterious force nudging the system towards higher entropy. It's just that higher entropy is always statistically more likely. That's why entropy has been called time's arrow. If energy has the opportunity to spread out, it will.
Good. So now think for a second about when I talked about your keeping your room neat or whatever, right? So it said if energy has the opportunity to spread out, it will. So if you had to live in a tiny house, okay, you wouldn't have the opportunity to spread your stuff out very much, right? You would kind of be forced to keep yourself organized or you lose your mind, right? But if you lived in a big house all by yourself, and you dropped your keys on the counter, they wouldn't be too hard to find the next day, left your shoes on the floor, right? If you have the opportunity to spread out your mess, I bet you do. Would I be wrong? Yeah. So I used to have a messy room fairly often when I was a kid, but what changed me was when I went to college, I had an option to get a roommate or an option to get a single room. And since I didn't grow up with any siblings and didn't quite know how I feel about it, I got myself a single room. And it was so tiny. Like the whole room was, the whole room was probably a little smaller, maybe about the size of this space we're in. That was everything, right? But it had a bed. It was actually probably a little smaller than this because it had a bed and then it had like the dresser and everything in the closet was all built in and the shelves were built in. It was pretty itty bitty. And I learned very, very quickly my freshman year of college that if I wasn't organized, I was going to lose important things. Like I would go to class without something I needed. So I was forced to be organized. I didn't have the opportunity to spread out, right? That's what happens if you're forced to be organized, put you in a tiny place. The smaller your room or the smaller your space, the less spread out you will be. So that was your homework assignment, was to explain why heat energy always transfers from a higher temperature to a lower temperature and never a lower to a higher. Was everybody able to come up with some kind of answer for that? Something?
Yes.
Good. Very good. So next week, I meant to show you this and I didn't open it. Let me open it real quick. Next week, we are moving on to, oops, I don't want to show you mine. Mine has answers in it. Here we go. So next week, we're going on to lesson 20, and lesson 20 is going to start looking like you've had before. It's a book lesson. And we're gonna move into gas behavior. And you have a lab at home for next week too, Jocelyn. And then you're
Yeah.
gonna have a whole bunch of kind of back to back. We're gonna have some more complicated labs that there will have to be videos for. I tried to squeeze in. I may be able to find some fun experiments at home that you can do, Jocelyn, but when we get to the acid and base stuff, we're gonna do a lot of titrating in the next couple weeks. And what that involves are these really, really cool lab apparatus. It's called, they're called burettes. So you know how you have your graduated cylinder and it might be like this tall and it might hold 50 milliliters because it's like this big around. Well, a burette is really tall, long, and it's tiny, narrow, and it might hold 50 milliliters, but it might be this long. And that's because it's very, very accurate. All the marks on it are super accurate. And drop by drop, we're gonna mix acids and bases together until we neutralize. But it's literally a drop by drop. You have to be very slow and deliberate. So we'll be getting into that in the next couple weeks. And I'll see if I can find some at-home stuff for those of you that are at home or who end up at home. I do think there's a chance in the next couple weeks we may see a shift in what the schools are doing, just based on numbers around here. So we're gonna be paying attention to it. But I know that now that we're at the like 2-week mark past when the holidays happened, this is kind of when I expect a boom. And then a lot of people are predicting another boom in March because it's nice. Again in March. I don't know, me too. But I got past my birthday because it's the beginning of the month. We didn't lock down until St. Patrick's Day. My birthday was already over.
It's almost up.
Yeah. This has been a strange, very strange year, but we're doing our best. So we're gonna move on to that. Next week, we're gonna move on to gases, and next week's experiment is another easy one. So Jocelyn,
Yes.
Senya, whenever you watch this back, after lab today, because it's a quick lab, we're gonna review balancing chemical equations. We're just gonna throw some up there on the screen. We have the board out. You guys can take turns balancing. You can practice balancing. And the reason we're doing that is because of all the stuff on the midterm, that's the one that was most bombed, was the one balancing chemical equation problem. A lot of people just bombed it. So I don't remember what it was exactly, but it was an equation to balance. And
No, I didn't do that one.
yeah, a lot of people just went,
no, I'm not doing that.
or just guessed. So we're gonna practice it again and again and again and again.
I actually did it out.
Yeah, so I will send out the link again for, do y'all remember we used this website, right? Whoops. We use this website right here, this one that says it's elemental, the balancing act. So we use this, and I'm gonna send this out again for everybody to practice with at home or whatever, okay? So we can tell Jocelyn so long. We're gonna head over to the lab now and hope.
Bye.
Bye, Jocelyn. Okay, y'all, let's go do our lab. You have her down. Ella, do you have a scrunchie or do you have a scrunchie? You got something? Yeah, you're gonna want to tie up. There's a flame today, so.
I think you. Do you want
Yes, I'm wearing it.
Yeah, turn your homework, not the,
This is the way I'll figure it out.
oh, just show it to me. Yeah, you can just show it to me. I know your mom had y'all do it. So, yeah, that's good. All right, cool. And I know she did it if
I
you
don't
did.
think I need these on here.
No, yours is okay, as long as you're not dangling it over the flame. You don't plan to do that, right?